Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. In the late 1950s and early 1960s, space exploration was still fragile, uncertain, and deeply constrained by fear of the unknown. Humanity had only just begun placing objects into orbit, and even the space between Earth and the Moon remained largely theoretical territory. The solar system beyond Mars was not merely unexplored, it was actively avoided. Engineers and scientists did not lack curiosity, but they lacked confidence. The region between Mars and Jupiter, known as the asteroid belt, was widely believed to be dangerous, possibly impassable, filled with debris dense enough to shred any spacecraft that attempted to cross it. This fear was not irrational. At the time, telescopes could not resolve the fine structure of the asteroid belt. What little was known came from indirect observation and incomplete models. The belt was understood to contain countless rocky bodies, remnants of planetary formation, but their distribution and spacing were unknown. Some scientists speculated that collisions were frequent and unavoidable. Others feared clouds of dust that could erode spacecraft surfaces or damage instruments beyond repair. Before humanity could even consider visiting the outer planets, it first had to answer a simpler question. Could a machine survive the journey at all? The Pioneer program emerged from this uncertainty. Unlike later missions designed to explore many worlds in sequence, Pioneer had a more modest and fundamental goal. It was not built to conquer the solar system, but to test whether the path outward was survivable. The mission was conceived during a period when spaceflight was still experimental, when every launch carried the risk of catastrophic failure, and when long-duration missions were unproven. Pioneer was meant to be simple, resilient, and honest in its limitations. Early Pioneer missions focused on near-Earth space and solar observation, gradually building confidence in spacecraft design and deep space communication. By the end of the 1960s, advances in rocketry, navigation, and radio technology made it possible to consider something bolder. For the first time, engineers could realistically aim a spacecraft toward Jupiter, the largest and most massive planet in the solar system. Jupiter was not only distant, but hostile. surrounded by intense radiation belts that no spacecraft had yet encountered. Reaching it would test every assumption about spacecraft durability. Pioneer 10 was conceived as the first attempt to cross the asteroid belt and reach Jupiter directly. Its mission was not primarily scientific in the modern sense. It was exploratory and diagnostic. It would measure particle densities, radiation levels, magnetic fields, and micrometeoroid impacts, providing data that would answer whether future missions were even possible. In many ways, Pioneer 10 was a scout, sent ahead to determine whether the road beyond Mars was open or closed. At the same time, scientists were becoming increasingly interested in Jupiter itself. As the largest planet, it held clues to the formation of the solar system. Its immense gravity influenced the orbits of asteroids and comets, shaping the architecture of planetary space. Studying Jupiter up close promised insights into atmospheric physics, magnetic fields, and planetary interiors on a scale never before observed. Pioneer offered a chance to study Jupiter while simultaneously proving that such exploration could be done safely. The political context of the era also played a role. The space race between superpowers created pressure to demonstrate technological capability, but Pioneer occupied a quieter space within that competition. It was not a race to land humans or plant flags. It was a demonstration of patience, planning, and scientific restraint. Pioneer missions were relatively inexpensive compared to crude programs, yet they carried enormous symbolic weight. They represented a willingness to send machines far beyond immediate utility, simply to learn. Pioneer 11 was conceived shortly after Pioneer 10, not as a duplicate, but as a refinement. Where Pioneer 10 would blaze the trail, Pioneer 11 would take advantage of the knowledge gained, adjusting its trajectory to attempt an even more ambitious goal. If Pioneer 10 survived Jupiter, Pioneer 11 might attempt to visit Saturn. This was a daring idea at the time. Saturn was even farther away, its rings poorly understood, and its gravitational influence complex. Yet the possibility existed, and Pioneer 11 was built with that possibility in mind. Both spacecraft were designed with extreme simplicity. They were spin-stabilized, meaning they rotated slowly to maintain orientation, reducing the need for complex attitude control systems. Their instruments were limited but robust. Power was supplied by radioisotope generators, chosen because solar panels would be ineffective at great distances from the sun. Every design choice reflected caution rather than ambition. Pioneer was built not to impress, but to endure. Perhaps most importantly, Pioneer was built without any expectation of return. These spacecraft were not designed to orbit planets or come home with samples. They were meant to pass through, observe, and continue onward. This concept marked a shift in how humanity approached space. For the first time, machines were being sent on trajectories that would never intersect Earth again. Pioneer represented acceptance of one-way journeys, guided by physics rather than retrieval plans. The decision to send Pioneer outward was, at its core, a decision to trust understanding over fear. The asteroid belt would either destroy the spacecraft or reveal itself as navigable. Jupiter would either overwhelm the instruments or allow them to pass. There was no way to simulate these conditions fully on Earth. Pioneer had to go first, carrying with it both scientific instruments and the unanswered questions of an entire field. In choosing to build and launch Pioneer 10 and 11, humanity took its first deliberate step toward becoming an interplanetary species of machines. These spacecraft were not explorers in the romantic sense. They were quiet testers of limits, sent to discover whether the solar system beyond Mars was accessible at all. Everything that followed, Voyager, Galileo, Cassini, New Horizons, depended on the answers Pioneer would provide. Before images, before discoveries, before silence, Pioneer was an experiment in possibility. It asked a simple question with far-reaching consequences. Can we go farther? And then it began to find out. When engineers began designing Pioneer 10 and Pioneer 11, they were not trying to build the most capable spacecraft possible. They were trying to build the most reliable one. At the time, deep space engineering was constrained by limited computing power, fragile electronics, and incomplete knowledge of the environments beyond Mars. Every added system increased the chance of failure. Simplicity was not an aesthetic choice. It was a survival strategy. The Pioneer spacecraft were designed around the principle of spin stabilization. Instead of relying on continuous thruster firings or complex control algorithms to maintain orientation, Pioneer slowly rotated around its central axis. This rotation created gyroscopic stability, allowing the spacecraft to keep its antennas pointed toward Earth with minimal intervention. The design reduced fuel consumption, minimized mechanical wear, and eliminated entire classes of potential failures. In deep space, where repairs are impossible, fewer moving parts meant longer life. Power generation posed one of the most serious challenges. Solar panels, effective near Earth, would become nearly useless beyond the orbit of Mars. Sunlight weakens rapidly with distance, and by the time Pioneer reached Jupiter, solar energy would be only a fraction of what it was near Earth. To solve this, engineers chose radioisotope thermoelectric generators, devices that convert heat from radioactive decay into electricity. These generators provided steady, long-lasting power, independent of sunlight, at the cost of limited output that could never be replenished. The choice of nuclear power shaped the entire spacecraft. Every system had to operate within strict energy budgets. Instruments were carefully selected and designed to consume minimal power. Heaters were limited, requiring components to survive extreme cold. Over time, as radioactive decay reduced available energy, systems would be shut down intentionally to preserve core functionality. Pioneer was built with the expectation of gradual simplification, not sustained peak performance. Communication was another defining constraint. Pioneer relied on a single high-gain antenna, permanently fixed to the spacecraft's body. There were no steerable dishes, no redundancy in pointing mechanisms. To transmit data back to Earth, Pioneer had to maintain precise orientation, aligning its antenna with distant receivers, using only spin and occasional thruster adjustments. Data rates were extremely low, even by the standards of the time, forcing scientists to prioritize what information mattered most. The onboard computers of Pioneer were minimal, even primitive. They lacked the memory and processing power of later missions, and were incapable of autonomous decision-making beyond basic sequencing. Observation schedules were prepared on Earth weeks or months in advance, uploaded to the spacecraft, and executed without feedback. Pioneer could not adapt to unexpected conditions. It could only follow instructions and report results. This limitation required extraordinary confidence in planning and modeling. Scientific instruments were chosen with equal restraint. Pioneer carried detectors for charged particles, magnetic fields, cosmic rays, and micrometeoroids. These instruments were not designed to produce detailed images or dramatic discoveries. They were meant to answer foundational questions. How intense is Jupiter's radiation? How dense is interplanetary dust? How does the solar wind behave at great distances? Pioneer was not built to amaze the public. It was built to inform future engineers. Thermal control presented another quiet challenge. In deep space, temperatures can fall close to absolute zero, yet electronics generate heat during operation. Pioneer relied on passive thermal management, using insulation, reflective surfaces, and internal heat distribution, rather than active cooling or heating systems. The spacecraft had to remain warm enough to function without wasting precious energy. This balance became increasingly delicate as power output declined over time. Radiation hardening was also essential. Jupiter's radiation belts were known to be intense, but their exact strength was unknown. Pioneer's electronics were shielded as much as possible, and critical components were positioned to minimize exposure. Even so, engineers accepted that some degradation was inevitable. Pioneer was built not to resist radiation completely, but to tolerate it long enough to complete its mission. Navigation and tracking relied entirely on Earth-based systems. Pioneer carried no star trackers or autonomous navigation capabilities. Its position and velocity were determined through precise measurements of radio signal frequency shifts, a technique known as Doppler tracking. By analyzing these signals, scientists could infer Pioneer's motion with remarkable accuracy, allowing course corrections to be calculated and uploaded from Earth. This method required extraordinary patience, as even small adjustments took weeks to plan and execute. The overall structure of Pioneer reflected its philosophy. A central body housed electronics and power systems, while instruments extended outward on booms to reduce interference. The high-gain antenna dominated its appearance, a constant reminder that communication was the spacecraft's lifeline. There was no redundancy in most systems. If something failed, it failed permanently. This was not recklessness. It was an acknowledgement of technological limits. Perhaps the most remarkable aspect of Pioneer's design was its acceptance of silence. Engineers knew from the beginning that communication would eventually end. Power would decline, systems would shut down, and the spacecraft would drift onward without contact. Pioneer was not built to be maintained indefinitely. It was built to function long enough to answer essential questions, and then to continue silently, carrying its trajectory forward. In designing Pioneer 10 and 11, engineers were not trying to create immortal machines. They were trying to create honest ones, spacecraft that reflected the realities of deep space and the limits of human engineering. Pioneer was a bridge between cautious experimentation and bold exploration. It demonstrated that survival beyond Mars was possible, not through complexity, but through restraint. This philosophy would echo through every mission that followed. Voyager, Galileo, Cassini, and New Horizons all inherited lessons first learned through pioneers' minimalism. Before humanity sent machines to explore the outer solar system in detail, it first learned how to let them endure. And endurance, more than ambition, was the true design goal of Pioneer. When Pioneer 10 and Pioneer 11 were prepared for launch, the missions carried an unusual addition that was not required for navigation, communication, or science. Attached to each spacecraft was a thin metal plaque, designed not for engineers or scientists, but for any intelligence that might one day encounter the spacecraft, long after its mission had ended. This decision was not driven by expectation. It was driven by reflection. The Pioneer plaques were not messages sent with confidence of reception, but artifacts placed with humility, acknowledging that once the spacecraft left Earth, it would travel far beyond human supervision. The idea of the plaque emerged during a period when humanity was becoming increasingly aware of its place in the universe. The late 1960s and early 1970s were marked by rapid advances in astronomy, biology, and planetary science. For the first time, it was becoming clear that Earth was not central, not unique in position, and perhaps not unique in potential. Against this backdrop, the notion of including a symbolic message aboard Pioneer felt less like science fiction and more like a quiet, philosophical gesture. The plaques were designed by a small group of scientists and communicators who faced an extraordinary challenge: how to convey information about humanity and its origin without relying on language, culture, or shared assumptions. There could be no written explanation, no audio playback, no decoding instructions. Whatever was placed on the plaque would need to stand alone, understandable only through universal principles such as mathematics, physics, and biology. This constraint shaped every design choice. At the top of the plaque, a diagram represented a transition of the hydrogen atom, chosen because hydrogen is the most abundant element in the universe. This transition defined a unit of length and time, establishing a reference scale that did not depend on human conventions. By anchoring the plaque's measurements to fundamental physical properties, the designers attempted to create a bridge between unknown observers and known laws of nature. The assumption was simple but profound. Physics, wherever it is practiced, follows the same rules. The plaque also depicted the position of the sun relative to nearby pulsars, using the unique radio emission periods of these rapidly rotating neutron stars as cosmic landmarks. Each pulsar's period was encoded in binary, providing both identification and a timestamp. Because pulsar periods change predictably over time, the diagram could, in principle, allow an observer to determine when the spacecraft was launched. This element of the plaque embedded the Pioneer missions not just in space, but in time. Perhaps the most discussed feature of the plaque was the representation of the human form. A simplified outline of a man and a woman stood beside a schematic of the spacecraft itself, providing a sense of scale. The figures were intentionally neutral, stripped of cultural markers, clothing, or expressions. Their posture was calm, neither aggressive nor submissive, The goal was not realism, but clarity. This was not meant to depict individuals, but a species. The inclusion of the human figures sparked debate even before launch. Some questioned whether such representations were appropriate or safe. Others argued that the figures were too abstract, or too literal, or too culturally biased. Yet the decision was made to include them, not because they were perfect, but because they were honest. The plaque did not attempt to hide humanity behind symbols alone. It showed what we are, at least in physical form, without embellishment. Equally important was what the plaque did not include. There were no political symbols, no references to nations, no indication of conflict or hierarchy. There was no claim of ownership, dominance, or intent. The plaque did not ask for contact or offer instruction. It simply stated presence. In this restraint, the plaque reflected the broader philosophy of the pioneer missions themselves. Observe, measure, and move onward without interference. The plaques were engraved on anodized aluminum, chosen for its durability and resistance to corrosion. Engineers expected the plaques to survive far longer than the spacecraft's electronics, enduring radiation, micrometeoroid impacts, and extreme temperature variations. Long after Pioneer's transmitters fell silent, the plaques would remain, attached to machines drifting endlessly through space. They were built not for decades, but for millions of years. Importantly, the plaques were not added with the expectation that they would ever be found. Space is vast, and the probability of an encounter is vanishingly small. The plaques were not a communication strategy. They were a statement of perspective. They acknowledged that humanity, even at an early stage of technological development, was capable of thinking beyond immediate utility and considering its long-term imprint on the cosmos. In this sense, the pioneer plaques were as much messages to ourselves as to any hypothetical observer. They reflected how humanity chose to present itself when stripped of context and urgency, not as conquerors, not as masters, but as beings aware of their origin, their scale, and their fleeting moment in time. The plaques asked no questions and offered no answers. They simply existed. As Pioneer 10 and Pioneer 11 departed Earth, the plaques went with them, unnoticed by the spacecraft, unremarked upon by their instruments. They were passive companions, silent and unchanging. Yet their presence transformed the missions from purely scientific endeavors into something quietly symbolic. The spacecraft were not just probes, they were carriers of memory. Long after the last signal fades, long after the missions are archived in human history, the plaques will continue onward, fixed to machines following trajectories shaped by gravity long ago. Whether they are ever seen or never encountered at all, their meaning does not depend on reception. It lies in the act of sending something outward, not because it will be answered, but because it represents a moment when humanity chose to acknowledge the vastness beyond itself. That choice, quiet and deliberate, travels with Pioneer still. Pioneer 10's launch was not merely the start of a mission, but the beginning of a test that spaceflight had never truly attempted before. By the early 1970s, humanity had proven it could reach the moon and send probes to nearby worlds. Yet the outer solar system remained a distant idea, separated by years of travel, weak sunlight, and environments no spacecraft had directly measured. Pioneer 10 was built to answer a blunt and practical question. Can a machine cross the asteroid belt, survive the journey to Jupiter, and return useful data across distances that make control slow and fragile? The launch, therefore, carried a specific kind of tension, because success would not be known in minutes or hours. It would be known over months, and then years, as the spacecraft steadily reported whether the unknown was survivable. Pioneer 10 launched on March 2nd, 1972, lifted by an Atlas Centaur rocket. The rocket choice mattered because the mission required more than simply reaching orbit. It needed to escape Earth's gravity and enter a solar orbit that would intersect Jupiter's path at the correct time. This is one of the quiet truths of interplanetary flight. Leaving Earth is not just about speed, but about timing and geometry. The spacecraft must be sent outward along a trajectory that arrives at the target planet when the planet is actually there, and the margin for error is not generous. A small mistake early becomes a large miss later, and while mid-course corrections can fix some drift, they cannot create energy that was never provided. The launch vehicle had to deliver Pioneer 10 onto an accurate path with enough speed that course corrections would remain minor, conserving fuel for the long cruise ahead. The first minutes of flight were violent compared to the mission's later calm. A deep space craft spends most of its life in silence, but it must survive launch vibrations, acceleration loads, and the rapid shift from atmospheric pressure to vacuum. Pioneer 10 had been tested for these stresses on Earth, yet the true test is always the real event. When the spacecraft separated from the final stage and the last controlled burn ended, the character of the mission changed instantly. There was no more climbing, no more engine roar, no more atmosphere. There was only a small, spinning spacecraft coasting away from Earth, carrying a fixed amount of energy and a direction that would now define its future. In the early days after launch, the mission team entered what is often called commissioning, a phase where a spacecraft proves it is alive in space as a complete system rather than a set of tested parts. Pioneer 10's high-gain antenna needed to lock onto Earth, its transmitter needed to hold a stable signal, and the spacecraft's spin needed to remain within a safe range. Engineers listened to telemetry that seemed mundane, but was essential. Temperatures, voltages, currents, and the health of subsystems that would be difficult or impossible to repair by command if they drifted into unstable behavior. Each small confirmation mattered because deep space missions are won not by dramatic moments, but by continuous stability. Navigation began immediately, even though the destination was still far away. Earth-based tracking relied on radio science. Signals sent to the spacecraft and returned were examined for minute frequency shifts, allowing engineers to infer velocity along the line of sight using the Doppler effect. Combined with precise models of Earth's own motion and the spacecraft's expected trajectory, this allowed the mission team to estimate Pioneer 10's path with remarkable accuracy. Yet, accuracy in deep space is always probabilistic. It is an envelope of possible positions that shrinks with better data and grows with uncertainty. The art of navigation is deciding when the envelope is too large and when a correction burn is justified. Thrusters on Pioneer 10 could adjust its speed by only small amounts, but a small change applied early can shift arrival geometry at Jupiter by thousands of kilometers. So the mission planned these burns carefully, slowly, and conservatively. As Pioneer 10 traveled outward, it moved through regions of space that were already familiar in principle, but not yet familiar in measurement. The solar wind, charged particles streaming from the sun, flowed past the spacecraft continuously, carrying the sun's magnetic field outward. Instruments measured particle densities and energies, tracking how the solar wind changed with distance and time. These measurements were not just background noise. They helped scientists understand how the sun influences the space between planets, how radiation environments vary, and how a spacecraft might be affected as it moves farther from solar protection. Pioneer 10 was accumulating a kind of quiet map, not of terrain, but of conditions. Then came the asteroid belt, the symbolic barrier that had haunted early mission design. In reality, the belt is immense and mostly empty, but proving that with direct passage mattered. Pioneer 10 crossed through the region between Mars and Jupiter without incident, and in doing so, it provided something more valuable than reassurance: data. Detectors measured micrometeoroid impacts and particle populations, showing that the density of debris was not high enough to make the passage suicidal. This shifted the psychological and technical landscape of mission planning. Future spacecraft could be designed with realism rather than fear. The belt was not an obstacle course. It was a wide region of space with sparse hazards, manageable through standard shielding and cautious design. Throughout the cruise, Pioneer 10's spin stabilization continued to do its quiet work. The spacecraft's rotation helped maintain orientation and thermal balance, and it reduced the need for frequent attitude adjustments. This mattered because each thruster firing consumed fuel, and fuel in deep space is not simply propellant, it is lifespan. A mission that wastes fuel early risks losing its ability to keep the antenna pointed later. That antenna pointing was not negotiable. Without it, data would stop, and the mission would become silent long before it reached its most important destination. So Pioneer 10's minimalism, its slow spin, its fixed antenna, its restrained maneuvering, was not primitive. It was deliberate engineering aligned with long survival. As Jupiter approached, the mission's true difficulty became clearer. Jupiter is surrounded by an intense magnetosphere filled with trapped particles. These radiation belts can damage electronics, corrupt data, and degrade sensors. In the early 1970s, their full intensity was not well known. Pioneer 10 was therefore both an explorer and a sacrificial scout, in the gentlest sense. It would go first, measure what it could, and reveal whether later, more ambitious missions could survive longer and collect more. The spacecraft's instruments began to record rising particle counts as it entered Jupiter's influence, confirming that the environment was becoming harsher and that the most dangerous parts still lay ahead. The approach also carried a gravitational story that would shape Pioneer 10's fate. As the spacecraft fell into Jupiter's gravity well, it accelerated, converting gravitational potential into speed. Even before any close flyby, this effect was measurable. After passage, as it climbed away, it would lose some of that speed relative to Jupiter, yet its trajectory relative to the Sun would be transformed. Jupiter's gravity would bend the spacecraft's path and, depending on the geometry, adjust its heliocentric speed. Pioneer 10 was not using Jupiter primarily as a slingshot in the later Grand Tour style, but it was still participating in the same physics. Planets can redirect and reshape a spacecraft's solar orbit without the spacecraft burning fuel. This principle would become central to later missions, but here, it was already present in the background, like a preview of what gravity could do. When you zoom out far enough, the launch of Pioneer 10 becomes more than a date and a rocket. It becomes a transition in human capability. Before Pioneer 10, the outer planets were largely theoretical targets. After Pioneer 10, they became reachable destinations, not because they became closer, but because the path to them became understood as practical. The mission's early crews demonstrated that deep space flight could be stable, navigable, and survivable over long times. It demonstrated that the fear of the asteroid belt was overstated. It demonstrated that a small, minimal spacecraft could remain in contact with Earth as the distance stretched into the realm of hours of light travel. Pioneer 10 continued outward with a quiet steadiness, following a path decided by rocket burns, gravitational mathematics, and patient tracking from Earth. Its spinning body carried instruments that measured not only the space it passed through, but also the confidence of those who planned future missions. Even before it reached Jupiter, Pioneer 10 had already changed the story of exploration by proving that the solar system's middle distances were not a boundary. They were a corridor. And as Jupiter grew larger in the spacecraft's sensors, the mission moved from proving the journey was possible to proving the destination could be endured, with each new measurement tightening the bridge between what humans could only imagine and what a machine could actually survive. When Pioneer 10 finally reached Jupiter in December of 1973, it entered an environment that had never been directly measured by a spacecraft. Jupiter was not simply a larger version of Earth or even Saturn. It was a fundamentally different kind of world, one whose gravity, radiation, and magnetic influence extended far into surrounding space. For decades, astronomers had studied Jupiter through telescopes, tracking its cloud bands and storms, yet everything beyond appearance remained speculative. Pioneer 10 was about to replace speculation with measurement. Long before the closest approach, Pioneer 10's instruments began registering dramatic changes. Particle detectors recorded sharp increases in radiation intensity, confirming that Jupiter's magnetosphere was immense and powerful. The spacecraft was now moving through regions filled with charged particles, trapped by Jupiter's magnetic field, spiraling at high speeds along invisible lines of force. Engineers on Earth watched telemetry carefully, aware that radiation damage could disable instruments or corrupt data. Each hour of survival mattered because it meant that more of the environment was being mapped rather than merely inferred. The radiation belts surrounding Jupiter turned out to be far stronger than those around Earth. Pioneer 10 measured particle energies that exceeded conservative estimates, revealing that Jupiter's magnetosphere posed a serious threat to spacecraft electronics. This discovery alone justified the mission, because it immediately influenced how future probes would be designed and shielded. Without Pioneer 10's measurements, later missions might have underestimated the hazard and suffered catastrophic failures. Instead, Pioneer 10 became a warning and a guide, defining the limits within which engineers could safely operate. As the spacecraft moved closer, Jupiter's immense gravity accelerated it rapidly. Pioneer 10's speed increased as it fell inward, reaching its maximum velocity near closest approach. This acceleration was not powered by engines, but by gravity itself, transforming potential energy into motion. After passing the planet, the spacecraft would climb back outward, yet its trajectory relative to the Sun would be permanently altered. Jupiter's mass reshaped Pioneer 10's path, sending it onto a hyperbolic escape trajectory that ensured it would never return to the inner solar system. The closest approach occurred at a distance of just over 130,000 kilometers above Jupiter's cloud tops. From this vantage point, Pioneer 10's instruments gathered data at a pace unmatched earlier in the mission. The magnetometer mapped the structure of Jupiter's magnetic field, revealing its orientation, strength, and variability. These measurements confirm that Jupiter's magnetic field is generated deep within the planet, likely by motion within a layer of metallic hydrogen created under extreme pressure. This insight reshaped understanding of giant planet interiors, connecting atmospheric observations with deep physical processes. Pioneer 10 also provided the first close-up measurements of Jupiter's atmosphere. Although it did not carry a high-resolution camera like later missions, its instruments detected temperature profiles, pressure variations, and energetic particles associated with atmospheric activity. These data showed that Jupiter's atmosphere is driven not only by solar energy, but by heat rising from within the planet itself. Jupiter was revealed as a world still cooling from its formation, radiating energy outward and sustaining powerful winds in the process. The mission also delivered humanity's first close-range images of Jupiter. These images were modest by modern standards, grainy, and limited in detail, yet they carried enormous significance. For the first time, Jupiter was not a distant disk or a painted globe. It was a world observed from nearby space, with visible curvature, depth, and texture. These images helped validate navigation accuracy and provided visual confirmation that the spacecraft had survived its passage through the radiation environment. Beyond Jupiter itself, Pioneer 10 collected valuable data about the surrounding space. Measurements of plasma, dust, and energetic particles revealed how Jupiter interacts with the solar wind, shaping a magnetosphere that deflects and traps charged particles. This interaction demonstrated that planets can influence space far beyond their physical boundaries, creating regions of control that rival small stellar systems. Jupiter was not isolated. It was dominant. One of the quieter but most important results of the flyby was confirmation that spacecraft could survive Jupiter's radiation belts long enough to conduct meaningful science. Pioneer 10's electronics experienced degradation, but they did not fail catastrophically. Instruments continued to operate, data continued to flow, and communication with Earth remained intact. This outcome changed mission planning permanently. It meant that future probes could be built to endure similar conditions with improved shielding and redundancy, opening the door to more ambitious exploration. As Pioneer 10 departed Jupiter, its speed relative to the Sun settled at roughly 17 kilometers per second, fast enough to escape the Sun's gravitational hold entirely. This speed was not chosen intentionally at launch, but emerged naturally from the gravitational encounter. Pioneer 10 was now on a one-way path outward, its future defined by inertia rather than mission design. From this point on, it would never encounter another planet closely. Jupiter had been both destination and turning point. The data returned from the encounter occupied scientists for years. Each measurement refined models of Jupiter's magnetic field, atmosphere, and interaction with the solar wind. Each confirmed or corrected assumptions that had guided earlier theoretical work. Perhaps most importantly, Pioneer 10 proved that Jupiter was accessible, not just visually, but physically, to spacecraft built with care and restraint. In hindsight, Pioneer 10's Jupiter flyby appears modest compared to later missions that mapped the planet in exquisite detail. Yet without this first passage, those later missions might never have flown. Pioneer 10 did not attempt to answer every question. It answered the most important one. Can we go there and survive long enough to learn something meaningful? As the spacecraft moved away from Jupiter, its instruments continued to record data, but the most intense phase of the mission had passed. The planet shrank behind it, and the radiation environment softened gradually. Pioneer 10 carried with it a transformed understanding of the solar system's largest planet and a newly earned confidence in deep space exploration. Jupiter had tested the limits of early spacecraft engineering and revealed those limits to be wider than feared. Pioneer 10 emerged not triumphant in any dramatic sense, but successful in the way that matters most in science. It replaced uncertainty with knowledge and made the unknown navigable for those who would follow. And with Jupiter behind it, Pioneer 10 continued onward, quietly becoming humanity's first object, truly on its way beyond the familiar planets, carrying lessons learned from the giant that reshaped its path. Pioneer 11 was never intended to simply repeat the journey of Pioneer 10. From its earliest planning stages, it was conceived as a response, an adjustment informed by what Pioneer 10 would discover. Where Pioneer 10 was sent to answer whether Jupiter could be reached and survived, Pioneer 11 was designed to test whether that success could be extended farther. Its mission would depend almost entirely on the outcome of Pioneer 10's encounter, making Pioneer 11 a spacecraft that launched with possibility rather than certainty. Launched in April of 1973, Pioneer 11 followed a trajectory similar in principle to its predecessor, but distinct in execution. Its path was carefully shaped to arrive at Jupiter later, allowing mission planners to incorporate lessons learned from Pioneer 10's flight. This staggered timing was not accidental. It reflected a philosophy of incremental risk, where each mission informed the next, reducing uncertainty step by step, rather than confronting all unknowns at once. During its cruise toward Jupiter, Pioneer 11 benefited from improved expectations. Engineers now knew that the asteroid belt was navigable and that deep space communication could be sustained over long periods. Yet new uncertainties replaced old fears. Pioneer 11's planned trajectory through Jupiter's system was far more complex than Pioneer 10's. Instead of a relatively distant pass, designed mainly to escape the solar system, Pioneer 11 would dive deeper into Jupiter's gravity well, using the planet's mass to bend its path sharply inward towards Saturn. This maneuver required extraordinary precision. Jupiter's gravity is immense, and small changes in approach angle or timing can produce radically different outcomes. Too shallow a pass would fail to redirect the spacecraft sufficiently. Too deep a pass could expose Pioneer 11 to radiation levels far beyond what its electronics could tolerate. Navigation teams on Earth spent months refining calculations, using updated models of Jupiter's magnetic field and radiation belts based on Pioneer 10's data. As Pioneer 11 approached Jupiter, its instruments once again recorded rising radiation levels, confirming the hostile nature of the environment. However, this time, the spacecraft passed closer to the planet than Pioneer 10 had. Particle detectors measured intense fluxes of charged particles, pushing instruments to their operational limits. Engineers monitored telemetry with heightened concern, aware that Pioneer 11 was venturing into regions only partially characterized by earlier data. The closest approach brought Pioneer 11 within a narrow corridor that balanced survival against trajectory control. Jupiter's gravity accelerated the spacecraft dramatically, increasing its speed while simultaneously bending its path downward relative to the plane of the solar system. This gravity assist was far more aggressive than Pioneer 10's, effectively turning Jupiter into a gateway rather than a destination. When Pioneer 11 emerged from the encounter, its future was no longer defined by escape alone. It was now aimed squarely towards Saturn. The success of this maneuver was a defining moment in interplanetary navigation. For the first time, a spacecraft had used one planet, not just to leave the solar system, but to reach another distant world. This was not a coincidence or a bonus outcome. It was deliberate exploitation of gravity as a navigational tool. Pioneer 11 demonstrated that planetary flybys could be chained together, each shaping the next leg of a journey through careful planning rather than propulsion. After Jupiter, Pioneer 11 entered a long cruise phase towards Saturn, traversing a region of space still largely unmeasured. Instruments continued to record solar wind properties, cosmic rays, and magnetic field variations, contributing to a growing picture of how space changes with distance from the Sun. Meanwhile, communication delays increased steadily, forcing mission planners to accept longer gaps between command and confirmation. Operations became more about anticipation than reaction. Approaching Saturn, Pioneer 11 faced another layer of uncertainty. Saturn's ring system, visible from Earth, was poorly understood in structure and thickness. Some scientists worried that the rings might consist of dense debris, capable of damaging or destroying a spacecraft passing through or near them. To minimize risk, Pioneer 11's trajectory was designed to pass below the rings rather than through them, threading a narrow path between the planet and its innermost ring structures. As Pioneer 11 neared Saturn in 1979, its instruments began detecting the planet's magnetic field and surrounding plasma environment. Saturn's magnetosphere proved to be gentler than Jupiter's, but still complex. Measurements revealed differences in field strength, orientation, and interaction with the solar wind, highlighting how planetary magnetic systems vary even among giants. These data would later prove crucial for planning the Voyager missions, which would approach Saturn with far greater ambition. The Saturn flyby itself marked the farthest point any human-made object had reached at that time. Pioneer 11 became the first spacecraft to visit Saturn, returning images and measurements that transformed understanding of the planet and its rings. Though its imaging capabilities were limited, the data confirmed that Saturn's rings were thin and composed of countless individual particles rather than solid sheets. This finding eliminated a major concern for future missions and opened the door to closer, more daring exploration. Perhaps most importantly, Pioneer 11 proved that gravity assists could be used not just once, but repeatedly to traverse the solar system. Its journey from Earth to Jupiter and onward to Saturn established a new paradigm for mission design, one that treated planets as stepping stones rather than endpoints. This approach would later enable the Voyager Grand Tour, allowing a single spacecraft to visit multiple planets using carefully timed flybys. As Pioneer 11 departed Saturn, it did so on a trajectory that, like Pioneer 10's, would never bring it back. Its path was now defined by inertia and gravity, carrying it steadily outward into the far reaches of the solar system. Communication would continue for years, but the most dramatic phase of the mission was complete. Pioneer 11 had extended humanity's reach beyond what Pioneer 10 alone could accomplish. Together, Pioneer 10 and Pioneer 11 transformed exploration from isolated missions into connected journeys. Pioneer 10 showed that Jupiter could be reached and survived. Pioneer 11 showed that Jupiter could be used as a bridge to even more distant worlds. This pairing, modest in scale but profound in consequence, laid the foundation for everything that followed. As Pioneer 11 moved away from Saturn, it carried with it not only data, but proof that the solar system could be navigated deliberately and patiently, one gravitational step at a time, with machines built to endure rather than impress. After Pioneer 11's encounter with Saturn, both Pioneer spacecraft entered a region of space that, even today, remains largely unvisited. Beyond the orbit of Saturn, the solar system changes character. Distances between objects increase dramatically. Sunlight weakens, and the sense of motion becomes subtle rather than immediate. For Pioneer 10 and Pioneer 11, this phase of the journey was not marked by new destinations, but by endurance, consistency, and the slow accumulation of data over immense spans of time. From an engineering perspective, the missions entered what might be called the long tail of exploration. The spacecraft were no longer approaching major planets, and therefore no longer required precise targeting for close encounters. Instead, their task became one of sustained measurement. Instruments continued to sample the solar wind, cosmic rays, and magnetic fields, providing a continuous record of how these phenomena evolve with distance from the sun. This continuity was itself valuable because it revealed patterns and cycles that short missions could never observe. As the spacecraft moved farther outward, the sun became a less dominant presence. Solar radiation pressure diminished, thermal input decreased, and power margins tightened further. Engineers responded by making gradual operational adjustments, carefully balancing power usage against scientific return. Instruments were turned off one by one, not because they failed, but because preserving communication and core measurements became more important than maintaining full capability. This process unfolded slowly, over years, reinforcing the idea that deep space missions do not end abruptly, but fade in carefully managed stages. Communication grew increasingly fragile. Signals weakened as distance increased, spreading thin across the vastness of space. Receiving stations on Earth relied on large antennas and long integration times to extract usable data from the noise. Each transmission required patience, both from the spacecraft and from the teams listening on Earth. The conversation between planet and probe became stretched, measured not in seconds, but in hours of light travel. Commands sent in anticipation would be acknowledged long after the context that prompted them had passed. From the spacecraft's point of view, nothing changed suddenly. Pioneer 10 and Pioneer 11 continued to spin, continued to point their antennas toward Earth, and continued to execute their limited instructions. There was no awareness of milestones, no recognition that they were moving beyond the last giant planet. Yet from a human perspective, this phase represented a quiet threshold. These were the first machines to travel so far from the sun that planetary encounters were behind them, and interstellar space lay ahead as an abstract destination rather than an imminent one. Scientifically, this region revealed itself through subtlety. Particle densities declined. The solar wind became less turbulent. Magnetic fields weakened and shifted orientation. These changes were gradual enough that they required long-term observation to interpret. Pioneer's instruments recorded not dramatic spikes, but trends, slow, persistent transformations that described how the sun's influence thins with distance. This data later became crucial for understanding the heliosphere, the vast bubble carved by the solar wind into the surrounding interstellar medium. Cosmic rays, high-energy particles originating beyond the solar system, became increasingly prominent. As the sun's magnetic shielding weakened, more of these particles reached the spacecraft. Pioneer's detectors measured their energies and directions, contributing to knowledge about radiation environments that future interstellar missions would need to consider. These measurements were not about single events, but about background conditions, the kind of information that defines whether long-term survival is possible. Emotionally, though no one would have used the word at the time, the missions entered a quieter relationship with Earth. There were no flyby images to release, no major discoveries to announce. Public attention shifted elsewhere, yet within scientific circles, the data continued to arrive, steady and reliable. Pioneer became a reminder that exploration is not always dramatic. Often, it is patient and repetitive, valuable precisely because it continues when novelty fades. As years passed, the spacecraft moved farther apart from one another as well. Pioneer 10 and Pioneer 11 were not traveling in formation or toward the same region of space. Each followed its own trajectory, shaped by gravity encounters long past. Their separation emphasized another truth of deep space. Once launched, spacecraft do not remain companions. They diverge, each tracing a unique path through the solar system's outskirts. Eventually, Pioneer 10 crossed the orbit of Uranus, then Neptune, not by visiting them, but by passing their orbital distances. Pioneer 11 followed a different route, influenced by its Saturn encounter. These crossings were symbolic rather than operational. The planets themselves were nowhere nearby. Yet passing these distances underscored how far the spacecraft had traveled, moving from a world where planets dominate navigation to one where distance itself becomes the defining feature. Power continued to decline. Instruments fell silent. Heaters were turned off. Systems were simplified further. Communication sessions became shorter and less frequent. Engineers knew from the beginning that this would happen. Pioneer was not designed to last forever. It was designed to last long enough. And in doing so, it exceeded expectations, continuing to operate years beyond its nominal mission life. What remained constant through all of this was motion. Pioneer 10 and Pioneer 11 continued outward, each year carrying them farther from the sun than any previous human-made object. Their speed, imparted by rockets and gravity assists long ago, did not diminish. There is no friction in deep space to slow them meaningfully. Their journeys were no longer active missions in the traditional sense, but trajectories, long arcs extending outward through a region few would ever experience directly. By the time communication finally faded, Pioneer had already accomplished its most important work. It had demonstrated that spacecraft could survive not just brief encounters, but decades of isolation. It had shown that the solar system's outer regions were accessible, measurable, and navigable. It had quietly redefined what it means for a mission to succeed, shifting the focus from endpoints to endurance. Beyond Saturn, beyond public attention, and beyond easy storytelling, Pioneer continued into darkness. Its data became a foundation rather than a headline. Its legacy became structural rather than dramatic. And in that quiet persistence, the Pioneer missions achieved something rare in exploration. They taught humanity how to keep going when there is nothing left to see, only distance left to cross. The spacecraft did not need an audience to justify their motion. They carried forward because they had been built to do so, and because the physics that launched them continued to apply long after the last command was sent. In the vast, thinning space beyond the planets, Pioneer became less a mission and more a statement about patience, reliability, and the long arc of curiosity that does not require applause to endure. The silence of Pioneer 10 and Pioneer 11 did not arrive suddenly, and it did not feel like failure. It arrived gradually, in increments so small that each one seemed manageable on its own. A slightly weaker signal, a slightly shorter transmission window, a little less data returned during each listening session. The end of contact was not a moment. It was a slow transition, unfolding over years as power declined and distance increased. From an engineering standpoint, the approach of silence had been anticipated from the very beginning. Pioneer's power source, based on radioactive decay, was reliable but finite. Each year, the amount of usable electrical energy decreased as the radioactive material lost strength. Engineers responded by shutting down systems in a deliberate sequence, preserving communication and core measurements for as long as possible. This process required careful planning because once a system was turned off, it could not be turned back on without consuming energy that no longer existed. Communication itself became an exercise in patience and precision. As Pioneer moved farther from Earth, the strength of its radio signal weakened according to well-understood physical laws. The signal spread out, becoming thinner and harder to distinguish from background noise. Receiving stations on Earth compensated by listening longer, integrating faint signals over extended periods, and coordinating between multiple antennas. Each successful reception became an achievement not of power, but of persistence. From the spacecraft's perspective, nothing dramatic occurred. Pioneer 10 and Pioneer 11 continued to spin, continued to transmit when commanded, and continued to operate within the limits of their remaining energy. There was no awareness of approaching silence, no change in behavior as the end drew near. The spacecraft followed instructions, executed sequences, and sent what data they could, indifferent to whether those signals were heard or not. For scientists, the gradual loss of contact marked the closing of an era. Pioneer had been returning data continuously for years, building long, uninterrupted records of particle environments, magnetic fields, and radiation levels. As instruments went offline, these records ended not with final conclusions, but with ellipses. Trends simply stopped being measured. Questions remained partially answered, not because they were unimportant, but because the tools to answer them had finally reached their limits. Public attention had long since moved on. By the time Pioneer 11's last signal was received in 1995, space exploration had entered a different phase. New missions were producing vivid images and complex data sets closer to home. Pioneer's quiet transmissions from the outer darkness no longer captured headlines. Yet within mission teams, each final contact carried weight, because it marked the end of a conversation that had lasted decades. Silence in deep space is not emptiness. Even after the transmitters fell quiet, Pioneer 10 and Pioneer 11 continued to move, continued to exist, and continued to pass through regions of space shaped by the sun and the galaxy beyond. Their instruments were no longer sending data, but their trajectories remained intact. The absence of communication did not mean the absence of presence. It simply meant that the link between Earth and spacecraft had finally stretched too thin to sustain. From a broader perspective, the silence of Pioneer marked a transition in how missions are remembered. While active, a spacecraft is judged by what it sends back. After silence, it is judged by what it accomplished while it could. Pioneer's achievements did not vanish when the signal stopped. The data already returned continued to inform models, influence mission design, and shape understanding of the solar system's structure far beyond Jupiter and Saturn. There is also a human dimension to this silence. Engineers and scientists who had worked with Pioneer for much of their careers experienced the end of contact as a quiet farewell. There was no ceremony, no countdown, no official termination. One day, the signal simply failed to rise above the noise. Attempts were made to listen again, to verify, to be certain. Eventually, the effort shifted from expectation to acceptance. The spacecraft had done what it could. Silence, in this context, is not loss. It is completion. Pioneer was never meant to report forever. It was meant to push outward until physics, not failure, set the boundary. That boundary arrived in the form of diminishing power and increasing distance, exactly as predicted. The mission ended, not because something broke unexpectedly, but because it followed the laws it was built to obey. Long after the last transmission, Pioneer 10 and Pioneer 11 remain in motion. They are still crossing space, still responding to gravity, still carrying the plaques attached to their frames. Silence does not erase them. It simply means they have passed beyond the reach of conversation. Their journey continues, indifferent to whether anyone is listening. In the end, the silence of Pioneer is not a disappearance, but a transformation. The spacecraft moved from being participants in an ongoing dialogue to being witnesses without voices. They no longer tell us what they see, but they still show us what is possible. That machines can be sent far beyond immediate usefulness, allowed to fade naturally, and trusted to carry their purpose forward even after contact ends. This quiet ending is not dramatic, but it is honest. It reflects the nature of deep space itself, where distances do not allow constant exchange, and where endurance matters more than presence. Pioneer's silence is therefore not an absence of meaning, but a confirmation of it. A reminder that exploration does not require perpetual attention to be real. When asking where Pioneer 10 and Pioneer 11 are today, the answer depends on how one chooses to measure distance, time, and relevance. These spacecraft no longer occupy a place that can be easily pointed to on a map or described with familiar reference points. They are far beyond the planets, far beyond routine navigation, and far beyond the range where human intuition works comfortably. To understand their current position, one must first abandon everyday scales and adopt the language of astronomical distance and light itself. Pioneer 10 and Pioneer 11 are both on escape trajectories from the Sun. This means that, unlike planets or comets bound to elliptical orbits, they will never return inward. Their paths are open-ended, shaped by gravity long ago, and now governed almost entirely by inertia. Each second, they move farther away, not because they are accelerating, but because nothing remains to pull them back. The Sun still influences them, but not enough to reclaim them. At their current speeds, Pioneer 10 and Pioneer 11 travel roughly 12 kilometers per second relative to the Sun. This is fast by human standards, faster than any aircraft, faster than Earth's orbital speed around the Sun when measured in straight-line terms. Yet on interstellar scales, this speed is gentle, almost contemplative. At this pace, it takes hours of light travel for signals to bridge the distance Pioneer once maintained with Earth, and thousands of years for the spacecraft themselves to approach even the nearest stars. When last contact was made, Pioneer 10 was already more than 80 astronomical units from the Sun, while Pioneer 11 was somewhat closer, but following a different trajectory. Today, estimates place Pioneer 10 well beyond that distance, moving steadily outward into the constellation Taurus. Pioneer 11 follows another path, angled differently relative to the plane of the solar system. These directions matter not because of where the spacecraft are headed, but because they illustrate how gravity sculpted each journey uniquely. To put their distance into perspective, consider light hours. Light, traveling at 300,000 kilometers per second, takes about 8 minutes to reach Earth from the Sun. Pioneer 10 is now so far away that light would take many hours to travel from the Sun to its current position. This means that sunlight arriving at Pioneer today left the Sun long before many events on Earth even began. The spacecraft exists in a delayed relationship with its origin, moving through a region where time itself feels stretched. Measured in light days, the distance becomes even more abstract. Pioneer 10 is several light days away from the Sun, meaning that light emitted at the Sun takes days, not minutes, to reach it. This framing removes any remaining sense of immediacy. Pioneer is no longer part of a system defined by rapid exchange. It occupies a realm where communication delays are measured in rotations of Earth, rather than moments of thought. Yet even light days are still small on cosmic scales. A single light year, the distance light travels in 1 year, is nearly 10 trillion kilometers. At Pioneer's current speed, reaching a distance of 1 light year from the Sun will take on the order of tens of thousands of years. This timescale is difficult to grasp because it exceeds recorded human history. Entire civilizations could rise and fall, while Pioneer continues to drift outward, unchanged in purpose and unaware of the passage of time. Over the next several thousand years, Pioneer 10 and Pioneer 11 will pass through the outermost fringes of the Sun's gravitational influence, including the region known as the Oort cloud. This distant reservoir of icy bodies marks the farthest extent of material loosely bound to the Sun. Even here, Pioneer will not encounter dense structures or dramatic events. Space remains mostly empty, and encounters are rare. The spacecraft will simply pass through, moving between objects separated by enormous distances. Beyond the Oort cloud lies true interstellar space, where the Sun's influence fades into the background of the Milky Way's gravitational field. Pioneer will enter this realm, not with ceremony, but by degree. There is no clear boundary, only gradual change. The density of solar particles diminishes, the background of galactic radiation grows more prominent, and the spacecraft becomes one of countless small objects orbiting the center of the galaxy. From a galactic perspective, Pioneer 10 and Pioneer 11 are not traveling towards specific stars. Their trajectories will not bring them close to any known stellar system for millions of years, if ever. Space between stars is vast beyond intuitive understanding. Even at high speeds, the chance of a close encounter is extremely small. Pioneer is not a messenger sent to a destination. It is a record of motion itself. This realization changes how we think about where Pioneer is. Its significance does not lie in its coordinates, but in its continuity. It is still moving. It is still obeying the same physical laws that governed its launch. It has not stopped, not slowed in any meaningful way, and not altered its course. In a universe defined by motion, this persistence is its defining feature. Even though communication ended decades ago, Pioneer 10 and Pioneer 11 remain part of the solar system's extended story. Their paths trace the shape of the Sun's gravitational reach and then extend beyond it, marking a transition from planetary space to galactic space. They are reference points, not for navigation, but for understanding how far human influence has extended physically, if not consciously. If one could observe Pioneer today, there would be little to see. The spacecraft are cold, silent, and dark. Their transmitters inactive, their instruments unpowered. Yet they still carry the plaques attached to their frames, still spin slowly, and still move through space with the same calm inevitability that has defined their journey since launch. Nothing dramatic has happened to them. Nothing needs to. In asking where Pioneer 10 and Pioneer 11 are now, we are really asking how far a single decision can travel. These spacecraft are answers in motion, stretched across decades and distances that defy everyday comprehension. They are no longer explorers in the active sense, but they remain artifacts of exploration, continuing outward long after the moment that set them on their way. Their location today is less important than their direction. They are going away from the sun, away from the planets, and away from immediacy. In doing so, they carry with them a quiet reminder that even small, simple machines can outlast attention, cross enormous distances, and remain meaningful without ever arriving anywhere at all. After the last signal faded, and Pioneer 10 and Pioneer 11 passed beyond the reach of communication, their journeys did not change in any visible way. There was no new phase, no transition event, and no final command that altered their motion. The spacecraft continued exactly as they had before, moving outward through space along trajectories determined decades earlier. What changed was not their behavior, but our relationship to them. They moved from being participants in an exchange to becoming silent objects whose existence must be understood through physics rather than conversation. Both Pioneer spacecraft are traveling on paths that will carry them far beyond the region where the sun dominates. Their speed, roughly 12 kilometers per second, relative to the sun, is a legacy of the launch energy and gravitational encounters that shape their early journeys. This speed is constant in practical terms. There is no engine to accelerate them further, and no medium to slow them down. In deep space, motion persists. Each year, Pioneer travels tens of millions of kilometers farther from the sun, not as an achievement, but as a consequence of inertia. To appreciate the scale of this motion, it helps to translate distance into time using the speed of light. Light leaves the sun and reaches Earth in about 8 minutes. It reaches the distance Pioneer once occupied in hours. As Pioneer continues outward, the light travel time from the sun to the spacecraft stretches from hours to days, and eventually to weeks. This framing reveals how far the spacecraft has gone, not by numbers alone, but by delay, by the growing separation between cause and effect. In terms of light days, Pioneer now exists in a realm where sunlight arrives long after it is emitted, where the warmth and energy that once shaped the inner solar system arrive as faint reminders rather than active forces. The spacecraft does not rely on sunlight, but its environment reflects the sun's diminishing influence. Temperatures drop, particle densities thin, and the space around Pioneer becomes more representative of the galaxy than of any particular star. Looking farther ahead, the distance of 1 light-year stands as a symbolic milestone. 1 light-year is not a destination Pioneer will reach quickly. At its current speed, approaching 1 light-year from the Sun will take tens of thousands of years. This timescale far exceeds recorded human history. It stretches beyond civilizations, languages, and institutions. Pioneer's journey therefore unfolds on a timeline where human presence becomes hypothetical rather than assumed. During these long ages, Pioneer will pass through the Oort cloud, a vast and sparsely populated region of icy bodies that marks the outermost fringe of material gravitationally associated with the Sun. Even here, encounters will be rare. The average distance between objects is enormous. Pioneer will not weave between bodies or navigate obstacles. It will move through emptiness punctuated by distant points, its path unaltered by events that are statistically unlikely to occur. Beyond the Oort cloud, Pioneer will enter interstellar space in a practical sense, becoming subject primarily to the gravitational influence of the Milky Way rather than the Sun. Yet even this transition is gradual. There is no clear line marking the end of the solar system's authority. The Sun's pull weakens slowly, blending into the collective gravitational field of nearby stars. Pioneer's motion becomes part of a much larger orbital pattern around the galactic center, shared with billions of other objects. Over millions of years, Pioneer's trajectory will curve gently as it orbits the Milky Way. It will not move in a straight line forever. Galactic gravity will bend its path, shaping it into a slow arc that reflects the structure of the galaxy itself. In this sense, Pioneer becomes a participant in a cosmic rhythm far larger than its original mission, carried along by forces that act on timescales beyond planning or prediction. The physical structure of the spacecraft will change slowly as well. Micrometeoroid impacts, though rare, will accumulate over immense spans of time. Cosmic radiation will alter materials at the atomic level. Thermal cycling will stress joints and surfaces. None of this will happen quickly. Pioneer is not fragile in the short term. It will persist far longer than any active system aboard it ever did, gradually aging in silence. The plaques attached to Pioneer 10 and Pioneer 11 will remain among the most durable components. Protected from corrosion and designed to resist radiation, they will outlast electronics by orders of magnitude. Whether they are ever seen by another intelligence is unknowable and irrelevant to their significance. Their presence is a record of intent, not expectation. They testify that the spacecraft was sent outward with awareness of time beyond usefulness. From a philosophical perspective, Pioneer's future forces a reconsideration of what it means to finish a mission. Pioneer did not complete its purpose when communication ended. Its purpose expanded. It became an object whose meaning lies in duration rather than activity. The spacecraft is no longer doing anything, yet it continues to be something, a physical trace of curiosity, carried forward indefinitely. There is a quiet symmetry in this. Pioneer was built to answer whether the outer solar system could be reached safely. In doing so, it demonstrated that machines could outlast attention, funding cycles, and even memory. Long after its builders are gone, Pioneer will still be moving, carrying with it a frozen moment from a specific era of human thought. If Pioneer is ever encountered, it will not announce itself. It will not signal or explain. It will simply exist, a small object in a vast field, its meaning legible only through interpretation. And if it is never encountered, nothing is lost. Its journey does not require witnesses to be real. In the end, the long drift ahead is not about arrival. It is about continuation. Pioneer 10 and Pioneer 11 will continue moving long after the concept of mission has ceased to apply. They will drift through regions where time is measured in geological and stellar scales, carrying no urgency, no purpose beyond motion itself. This is the final state of the Pioneer missions. Not silence as absence, but silence as endurance. A pair of machines released into the universe, trusted to keep going without supervision, carrying forward a decision made once, long ago, to see whether the path outward was open, and to follow it as far as physics allows.